In this highlight video, we're going to talk about reactivity. One of the things that I like about organic chemistry is that once we understand the chemical and physical properties about different functional groups, we can make predictions about their reactivity. In this video, we are going to focus on the parts of the molecule which will trigger reactivity. So we will identify electron-rich sites and electron-poor sites. These are often referred to as nucleophiles and electrophiles. Once we've done that, we'll be able to predict reactivity of those functional groups. In general, we'll look for heteroatoms and pi bonds, and these are the parts of the functional groups which will cause reactivity. Reactions often involve electron-rich species, like we said, are called nucleophiles, reacting with electron-poor species, which are referred to as electrophiles. Nucleophiles, the way we can identify them is that they have either lone pairs of electrons or pi bonds, and what they're doing in acting as nucleophiles is they're really acting as Lewis bases. Remember, Lewis bases are electron pair donors. Electrophiles, which often include either cations or atoms that are electron poor, are really acting as Lewis acids, which are electron pair acceptors. Examples of nucleophiles and electrophiles are shown on the slide. So like I said, we can either have pi bonds or heteroatoms. Heteroatoms are any atoms other than carbon or hydrogen that have non-bonding electrons. So we could have, let's say, a generic species. This is an electrophile, and each of those nucleophiles can react with this electrophile. The nucleophiles will be donating a pair of electrons. The electrophile will be accepting the electrons. So when we have pi bonds, it'll be the pi bond which is donating electrons to the electrophile. So we could have that as an alkene or an alkyne. If we have heteroatoms with non-bonding electrons, or lone pairs, then it's one of those pairs of electrons which will be donated to form a bond with the electrophile. So oxygen can do it. Nitrogen is common. And here's another example with oxygen. So hydroxide can also act as a nucleophile. All right, electrophiles are going to be those species which accept electrons. So there's going to be some part of that molecule that has either a full plus charge or a partial plus. So if we have polarized bonds like this carbon-chlorine bond, chlorine is more electronegative, so it pulls the electron density toward it. So it builds up a partial negative charge, leaving a partial positive charge on the adjacent carbon. So in this case, we could have our nucleophile donating its electrons to the electrophile. So the electron density reacts with the electron deficient site. Because that carbon will not be able to form additional bonds, it would have two hydrogens attached to it, it would break the bond to the chlorine. Okay? Protons are good electrophiles. All right, they don't have any electrons. Carbocations can accept electrons, and carbon-oxygen bonds also have a delta minus on the oxygen or a delta plus on the carbon. We know this hydrogen is also delta plus, and so a nucleophile here could either be reacting with the carbon that has the delta plus, or it could be reacting with the proton. So in each of these cases, we have an electron-rich species, the nucleophile, reacting with the electron-poor species, the electrophile. So let's look at a couple sets of or pairs of reactants and see if we can predict how they would react with one another. So in the first one, we see a proton as one of the reactants. We know that a proton cannot behave as a nucleophile because it has no electrons. And so the proton has to behave as the electrophile, meaning that this ketone over here is going to have to be the nucleophile. So let's look. We could have a pi bond there. We also have non-bonding electrons on the oxygen. So what we'll typically see is that the non-bonding electrons will act as the nucleophile. The H plus will be the electrophile. And really, this is just an acid-base reaction in this case. We will see the proton being attached to the oxygen. We'll have now a plus charge on the oxygen. So this is the way any of these carbon-oxygen double bonds can be protonated, right? These are called carbonyl groups, like we saw for the carboxylic acids. Let's take this off here. All right, so we have another carbonyl group down here, right? Remember what that was called? Okay, this is called an ester. And in this case, it's reacting with hydroxide. So, how is hydroxide going to act? Is it going to act as an electrophile or a nucleophile? Well, we saw before that because it has 3 pairs of non-bonding electrons and a full minus charge, hydroxide is going to act as a nucleophile, right? That leaves our ester being our electrophile. Okay, so the nucleophile has to react with the electrophile. Where is it going to react with that ester? Well, again, we have a delta minus charge on the oxygen, leaving a delta plus on the carbonyl carbon. We'd also have a delta minus over here, so that really builds up that delta plus on that carbonyl carbon. So hydroxide would react with the carbonyl carbon. Because that carbon can't hold any more electrons, those electrons would be pushed up onto the oxygen. We'll see a lot of these reactions next semester. So in this case, here's the part we already had, but now we have an O minus up here, and our hydroxide has been attached down here. All right, the next one, we have ammonia. Ammonia has a pair of electrons. It's going to make it be the nucleophile. This alkyl chloride has buildup of minus charge on the chlorine, leaving the carbon with a delta plus. And so ammonia is going to react with that carbon, minus going to plus. It's going to displace the chlorine because that carbon can't hold any more electrons. And so the chlorine ends up being replaced or substituted by the ammonia. We have Cl. The Cl took its electrons with it, so this is Cl minus, or chloride. Has a minus charge. The nitrogen, remember nitrogen when it has 4 bonds to it will have a plus charge. All right, the last one has a pi bond. All right, so the pi bond typically is going to act as a nucleophile. Okay, those pi electrons the pi bond is weaker than the sigma bond, and so those that bond is more easily broken. So that's the nucleophile. Here's our electrophile. We have a delta plus on the hydrogen, delta minus on the chlorine, and so the pi bond can react with the H plus and lose the chlorine. So let's put in these extra H's that were already there just so we don't get mixed up here. And let's draw our product. Okay, so we had one H. So the new H could go to either end of that double bond. I'll put it over here. We have one H left on the right side, so that's going to be a plus. We've generated a carbocation. Plus, we have Cl minus as our other product. Okay, so if we can predict the polarities and the chemical properties of these different functional groups, most of the reactions we're going to see are going to involve minus reacting with plus. So if we know the polarities, we can predict how these atoms will come together.